estimating the difference between two population means. And the first story I'm going to do is actually real data. I'm just trying to find where the story is. Here it is. And this is the average number of movies that people go to per year. And I have to accept this data is true, but it's kind of old. It was in September 2018, and then they updated it in 2019. So it's still it's a pre-COVID number. Obviously, when COVID took over, people going to the movies kind of died for a couple of years, right? So I guess that makes sense.
I believe then that would that makes it at least 10 years old.
Yeah. Well, not really. 2019 is just 3 years old.
I know, but if you include 2020, it's 10 years.
Okay. Right. Now, they have two populations. Iceland, would you believe, has the world record for the number of movies people go to in a year. And it's surprisingly small. Let me find a number. It's on average 4.84 times a year. And United States of America, which you probably, as I did until I read this article, thought that Americans would go to the movies a lot more. But the answer is actually 4.13. So let me make sure that I'm on the right page. We are. Now, they don't give me a standard deviation for these, so this bit I'm really just guessing. But I'm going to make it 1 in each case. And let's suppose I took a sample of 100 people from Iceland and 200 people from America, and I got the same results, right? So nothing has changed, right? So we did it today, right? So we found 100 Icelandic people, and how many movies did you watch in the last year? And they said, you know, the average came out about 4.5. That really means you only go to a movie like 3-4 times a year, which is kind of, I'm a big movie goer then, because before COVID, I used to see a lot more movies with my wife than that. But, you know, some people never see a movie, so I guess it averages out. So that's the guys that we've got. And we want to find out by finding, oh, excuse me, let's find a 99% confidence interval and see if there is actually enough difference here for that to actually be statistically significant. So we are going to have to find the standard error of x1 take away x2. And we are going to do that by s1 squared over n1 plus s2 squared over n2. I'll go to my calculator, and hopefully the batteries last enough time for that to happen. Square root of 1 squared divided by 100 plus 1, don't know why I'm squaring it, because 1 squared just 1 anyway, divided by 200. And the answer I get is 0.122, roughly. And we are going to make the assumption that this data is normal. And because I can make that assumption, I am allowed to use this formula. And it is x1 bar take away x2 bar plus or minus a certain multiple of the standard error. And this is where your memory comes in. Can anybody remember what the magic number for a 99% confidence interval was? right? We had 1.645, which was 90. We had 1.96, which was 95. But can anybody remember what the 99 one was?
Believe it's 2.576.
If you want to be really accurate, it is. And nothing wrong with what you just said. I'm just lazy and I'm calling it 2.58, right? 2.576.
I remember that off the top of my head. I didn't use my
Oh,
calculator.
that was well done, because that is one of the versions of the answer. There is another version that some textbooks use. It's 2.585, right? So I'm using the 2.58. So there's a few versions going around there. And so in this case, if you take that away from that, I should be able to do it in my head. It's 0.71, give or take 2.58 times this guy. And so it's going to be 0.71, give or take 2.58 times 0.122. And the answer I get is 0.315. And if we, well, if we, is it 531? Yeah, it's 315. If we subtract it, so we got 0.71, take away that number, we get nothing 0.395. And if we add it, we get 1.025. And I'm now just going to round this off to say one decimal place. So 0.4 to 1. So there is statistically a difference between number of times per month an Icelandic person watches a movie and the number of times per month an American would watch a movie. And that difference is somewhere between 0.4 and 1. Now, since these are all positive, isn't that evidence that Icelandic people watch it more than Americans, right? And we could say that with a really high degree of confidence. Would you agree 99% is maybe not quite sell your house and bet on it, but maybe sell your car, right? That's how comfortable you would be in winning that bet. And we are good. So I'm now going to take that same data and make different assumptions. When I did this data, the assumption was that the sample sizes were big enough, which I think are reasonable. But I was also making the assumption that these were normally distributed, right? Now that might be true and is actually true in a lot of situations, but it might not be true with movies. Couldn't it be skewed to the left or more likely skewed to the right? What do I mean by that? Couldn't you have an awful lot of Icelandic people who hardly watch any, and then you get people who go like every second night? That would be a very high skew to the right, okay? And couldn't the Americans be a double bump, right? A lot of young people go to the movies, but old people don't, right? So there's like a peak at the young and then whatever, things like that. In other words, the data is not normal. If the data is not normal, you can have problems by using this formula because it's assuming that the data is, and you're making an assumption that it's false. So you would go and you would do, quite naturally, you would do salt. But we're not going to do salt by hand because you have to really use, let me say it again, we're going to use a t distribution using salt. You can't really do the t distribution by hand because this funny magic number doesn't keep changing depending on the sample size, and you can't have an infinite number of unknown values. And secondly, we're going to talk about something that does happen occasionally in questions. So let me first nip over to WebAssign so we can do the salt button, because it really doesn't matter where I do the salt button, does it? Where is it? Come on, salt button. There you are. Just wanting a salt button. Any will do. Right, here is salt. And I'm going to make a confidence interval for the difference between these two fellas, right? So inferential statistics. Two sample T.
We
So
can't
first,
see screen.
You can. Oh, okay. Let's try. Where is it? Heck, is it gone? Let me do this one. What are you looking at right now? What can you see?
Salt.
Oh, good. Right. So you're saying salt. Right. Now, if I bring this guy over, are you saying this fella? Okay. So now I'll do it again. 2 sample T, right? Now, the first group had a mean of 4.84. And you should use the T distribution when, 1, the samples are dead small, right? 14 of this and 12 of that, right? Use salt. The T distribution means use salt, right? If you know for sure that the data is not a nice hill, right? It's not normally distributed. It's skewed left, it's skewed right, or it's just you don't have a name for it, but it's weird, right? Use salt for that. So here it's 4.84. The standard deviation is 1, and the sample size was 100. And then the second group, which is the Americans, in this case is 4.13. The standard deviation is 1, and the sample size in this case just happened to be 200. And then we do confidence interval. Now, there's a button here that I've never used before. Do you see this box here? Assume equal variance. You see that? Right. Maybe we can make it a little bit bigger because I don't know what size some of your screens are. There. Can you see it a bit better now, right? That button. You should never check that box unless the question specifically says to you, you can assume that the variances are the same. Would you agree in the one that I just gave you, weren't they both 1? So it's kind of reasonable to assume that they're the same, right? So if the 2 standard deviations are about the same, there's a bit of wiggle room. Can you imagine a question where one of them was 1.2 and the other was 1.3, right? They're close enough to count as the same. If one of them is 14 and the other is 22, you should never hit that box, right? So typically, if they tell you, you can assume that they're the same. Or when you look at the standard deviations, the 2 standard deviations are almost identical, will allow a tiny wiggle room. Then you hit that box. In this case, shouldn't we hit that box because they're both 1? And now we're going to generate the results. And we are going to do a 99%, so I almost forgot to change that. And let's see what the interval looks like this time. And the answer we got was 0.39 and 0.12. And I've screwed it up, I've scanned the wrong place. 0.39 and 1.02, which ends up being 0.4 to 1. And that's not what I wanted to see, but it's still true because, oops. Wasn't that the same interval we got the other method? All right, there we are. You see it? So when we used the T distribution, we got that. And we used the normal distribution. We also got that. And that's not a bad thing. I was hoping that this one would be a little bit different, right, from this one, just to show you that those 2 do make a difference. So the only argument I can give for why these 2 intervals ended up being pretty much the same. I bet you if I wrote the answer to like 4 decimal places, there'd be a little difference going on, right? I think what's happened here is that the samples are reasonably big, right? If this was 10 and that was 20, I think the intervals would have separated quite a bit. Because typically what a T distribution does is that it gives you a bigger interval than the normal does. And the reason why the T distribution gives you a bigger interval, if you're dealing with data that is weird or not normal, don't you have to make it a bigger interval to be 99% sure? That's essentially the reason, right? So, yeah, Sometimes you win, sometimes you lose. I was hoping that was different, but it's still correct. So let's return to our homework questions. And where's the next one I want to do? Whoops. Chloe has decided to join us. Shush, hey, go. Be a good girl. She is a pain right now. She's going to probably go under and bite something just because she is. Chloe, no. Okay, I think I'm set up now. Right, so we're going to go in and look at question 7 and just kind of show you all the different versions. And there's not too many questions to do, just essentially 7 and 8, and that's us. So each of the 63 students in a stats class used their non-dominant hand to print as many letters of the alphabet in order as they could do in 15 seconds. Quite fun to actually do that, but we won't have time, right? But you can imagine, in my case, my left hand, I'm just guessing. I'd probably get about 4, right? Now, let's see what happened. This data contains tons of information, right, that you would get in a program like SALT. This one isn't SALT, you can tell just by the way that it's written. But anyway, there are 29 females, and they did 12.57. Do you really think in 15 seconds you could do 12 and a bit letters? Because I'm not convinced. Anyway, they did that. Standard deviation is that. This number here we don't care about. 34 males in that one. So just looking at this data, even if they didn't tell me it was a t-test, which you can see it is, aren't those samples tiny? Don't you want at least, a reasonable number? So I know that you would be doing a t-distribution. Now they're comparing the male to the female, and the answer is a negative number, which makes sense. Because if you take 12 and subtract 13 from it, you're going to get negative 1.3. Here is a 95% confidence interval, and then some other stuff we don't care about. So when it says, what was the mean number of letters printed by females, don't you simply go here, and there's your answer. And what about for the males? Which I find very unlikely. I'll be sexist here. I think females would do this job better than males. I think if we got, a group of, females and males and said, do this, my gut feeling is that women tend to be more dexterous, right? They're able to do things a little bit, I think males are more clumsy. And it says, what is the difference? And that's this guy. So all we're doing in these questions is reading a table and writing down the numbers. We did one like this before, didn't we? So what's the confidence interval going to be? Well, it's negative this guy. And it goes all the way up to that guy. And then you do one of those sentences, right? I'm 90% confidence, or in this case, 95% confidence. Now it says draw a picture illustrating this. So this is a little bit new. Do you see that number negative 3.5 and this positive number 0.9? So I want a thing that starts at negative 3.9 and finishes at roughly 0.9. Would you agree it's that one there? Does that look right? Negative 3.5, positive 0.9. Can you see it? Now, that is a visual representation of all the numbers in that range. When you look at that, do you notice it contains 0, doesn't it? If an interval contains 0, does it not mean that there's not enough evidence to prove there's a difference? And that's what question D is about. Now, there's a salt button at the bottom. It says, find the value of the unpooled standard error. I haven't talked about that. And note that degrees of freedom for this problem are given as 60. Use salt to find the t-value. So we're going to have to find that, you know, that magic 1.96 guy, we're going to have to find that. But before we do that, let's find the unpooled standard error. So I'm going to hit salt again. And I'm going to have to move some windows around a minute. Here we go. Are you looking at salt right now? Okay. Inferential statistics. And we are going to start putting in the numbers here. So it's going to be a 2-sample T. The first one was 12.571. And the second number is the standard deviation, which is 4.206. And the third number was the sample size. And for the females, it was 29. And then if we go to the second one, which is going to be the males, it's 13.824. And the standard deviation in the table was 4.681. And the sample size is 34. And we want a confidence interval. And the confidence interval here was a 95. And the word unpooled data is now kicked in. If they had said equal variance, or another phrase that has the same meaning, pooled data, you would have checked that guy. Right, so pooling the data or assume equal variance has the same effect, right? You check that box. Unpooled data or variances not equal, you would leave it unchecked. So when I generate the results, the answer that we get for the standard error is that number there. Do you see it? That's where it was hidden. See that 1.12 and all the good stuff that goes with it. So let me copy that. Bring this guy over. And there you go. Now, what do they want? 3 decimal places? Okay. There's your answer to 3 decimal places. Now, the last question. It says, note that degrees of freedom are 60 and use salt to find the T-star that was used in finding this interval. So I'm going to have to go back and look at some numbers here. Actually, I'll go on the white screen and you'll just trust me that I'm reading the numbers. If you were going to write the formula down, it would look like this. X1 bar, take away X2 bar, plus or minus a magic t-score that we don't know, but that's the guy we're going to find, times the standard error of X1 bar, take away X2 bar. We already know that. The answer to that was negative 1.307. We already know that guy. We just found it a few moments ago. That number was 1.120. And we already know what the interval was. I'll just have to find it because I can't remember where it is. Oh, Cariba, where are you, interval? I've got too many windows open here. Is it here? No. Is it here? Oh, come on. Found it. Here it is. And the interval was 0.392 up to 1.028, right? So that is the interval. And so with all this information, we should be able to find t. So what I'm going to do is I'm going to take this guy and add this fellow. So negative 1.307, add the unknown t guy times 1.120 must be equal to this number, the upper limit. Does that make sense? When you add them, you get the big number, and when you subtract them, you get the small one. And I've decided to do the big one. Okay, anybody, any ideas where we go next? As long as you do it to both sides, it's okay, Ro.
Would you add 1.307 to the next side?
You would indeed. So this is adding these together. You get 2.335. And what would you do next?
Divide the 1.1.
Yeah. So we take this and divide by that 1.12 guy. And 2.335 divided by 1.12. And I am looking at 2.08. And they say the answer is 2.00. I'm not going to argue over it. It's pretty much the same guy. Right. Are we good? Now, let me show you a different way.
Sorry, I actually
Yes.
got lost somewhere.
Okay. So we got the formula for calculating the interval is this fella. I know that the difference between them is negative 1.307, and I know that the standard error is this guy. And we're trying to find what number this thing I'm calling T star is. So if you take this number and add this, you get this answer here. So I said, take this number and add this, and you should get that guy. Are we clear to there?
Wait, so hold on. So you took that negative number, added it to the t plus 1.1. So you added
It's
those
not
together.
plus t times. And you added these two together to get 1.028. Because we know that when you add them, you get the big answer, and when you subtract these two things, you get the smaller answer, right? So this interval came from here. And so I already know the interval. So I just said, okay, that must mean that these two added is equal to that number. And that's what this line here is saying.
Okay.
If you take a number and you add the margin of error, you get this guy. And this is essentially the margin of error. Right. Now, once you get to here, you add 1.307 to both sides and it gets you this. You then divide by 1.12 and you get that. And the answer I got here is 2.08 and the answer they got is 2.00. And the only explanation I can give for why they're a little bit different is probably that they did this to a lot more decimal places and only rounded off at the end. You know, the classic thing, if you round off too much, your answer is going to be a bit out. So I suspect that's essentially what happened. Okay. What? Okay, good. Right, and as I said, we're pretty much finished, except we have one last question to do. Perfect timing. Let me read this question to you. It's question 8. And volunteers have developed a code. You know that one where they developed the code? It's a common theme. You know, it's one of those stories that keep coming up. And we have two groups. One of them gets zinc. Oh, let's go into the white screen, make sure that's actually what's showing. One group is getting zinc and the other group is going to get a placebo. And in the 23 participants who took the placebo, let me do this again. Group 1 is going to be the placebo group. And group 2 is going to be the zinc group. That's what got me out. In the placebo, there was 23 people. And the average number of days that they had a cold was 7.6 days. And the standard deviation was 1.5 days for them. The zinc group, group 2, in this group, let's see if I can find it. The mean was only 1.5 days for them, and the standard deviation, the standard deviation was 1.5. It's me and my scanning. And I need to find somewhere how many people were in that group. So 25. Okay. So 23 people got a placebo. Their cold lasted forever and a day, and the standard deviation was 1.5. In the zinc group, 25 of their mean number of days was 4, and their standard deviation was 1.5. Question A asks us to calculate that. Question B is asking us to calculate that. Well, actually, both of these are A, right? That and that. And question B wants a 95% confidence interval. And it uses the word unpooled data. And then question C is essentially write that down as a sentence. Okay, I think I've got enough. So we're going to do this all on salt. Why didn't I use my normal, if you can hear me over the back, why didn't I use my normal equation? You know, the 1.96 guy. There we go. What information did kind of made me decide that this is going to be a salt, a T distribution question? The main rules for choosing it are sample size is small or the distribution is weird, right? There was no indication in the story that the distribution was weird, but weren't the samples 23 and 25 really small? So that's why I chose it. Small sample sizes, use salt, use a T distribution. So hopefully you are looking at question 8, the last one with the use salt button on it. Okay, so I'm going to click on that and I'm going to bring this guy over and we're going to do 2 sample T. And we're putting in the placebo first. So there was a mean of 7.6 days. And the standard deviation was 1.5. And there were 23 people in the placebo group. And the second one, there was a mean of 4 days. And the standard deviation was 1.5 days, and there were 25 people in that group. And we're going to do a confidence interval, and it's going to be 95. And they said the word unpooled data, right? So when it's unpooled, do I check that box or do I leave it alone? Which do
Leave
you
it
do?
alone.
Leave it alone. If they said it was pooled data, I would do it. If they didn't mention anything, because that could happen, the fact that both standard deviations is 1.5, wouldn't that make me want to assume equal variance, right? But they told me not to use it, so I'm not using it. And here we go. And the difference between the two, right, is 3.6. The standard error is 0.433 to 3 decimal places. The lower limit is 2.72727, and the upper limit is 4.473. Can you see that all the numbers I want are in salt, right? I just need to know where to look. So let's return, and I will have a word with my dog in a minute, I think, because we've got the people doing the gutters and he has decided that he doesn't want them. Right, so there is all the answers. The difference, the standard error, and this fella, right? So we're cool so far. Everything you want is pretty much in front of us. I will now return back to finishing off the last of the question. Okay, yeah, got all the answers, of course, which is a real distraction. Okay, so in here we would put the 3.6. Here we would put the standard error, 0.433. Well, actually, too late now, they want 4 decimal places, so can we pretend it was 331? You want your interval here, 2.727 to 4.473, right? So that's where all those go. Now, it then goes on and finishes off a couple of sentences. So complete the following sentences interpreting the interval that we just got. With 95% confidence, we can say that the population of cold sufferers represented by the sample taking zinc lozenges would increase or decrease the number of days where you had symptoms. So the group that took the zinc, more or less days with the cold, based on that interval.
Less.
Less. And somewhere between that number and that number. And those two numbers are the same because I forgot to type in this one. I am not good with distractions. So if you got a cold, go and get one. You can actually, you get them. I've seen them. If you ever been to Safeway and you look at places where if you've got a cold, isn't one of the things you can get is little zinc lozenges? You ever seen those things? Right. Evidently, if you get a cold, you can save yourself a couple of days, maybe as many as 4. Right. Your cold, recover quickly. Yes, it is evidence that the difference is, right? Because it does not cover 0. Remember, 0 is in the interval mean there's no evidence, you can't tell. Why is there evidence? Because it does not cover 0. And so zinc lozenges appear to be effective, right? So that's you finishing. And I think this is a very nice place for us to say bye-bye. Now, before you go, obviously you're going to do your thing. Monday is a holiday. So homework and the online tests are all going to be due midnight Monday. Okay, so you've got one more day to do everything. So for now, bye-bye. Make sure you put your name down. I'll hang about for any questions.
So no class Monday, right?
Correct, no class.
Thank you.
You're welcome. In you come, you noisy little buggers. What have you found today? Hi guys. Whoops. Oh, I've got the dumbest changing plans. Side here.
Yeah.
This it's green.
Yeah.
Do you want that white as well?
Oh, that's all good.
So, okay. That's going to be. Okay, thank you.
Tell you what, quit shaking everything, what the heck?
Oh God, no, don't even go there. I want to stay married. Right? If she comes out and says, I want it zigzag pink, that's what I'm going to tell you, right?
That's on there for you.
Zigzag pink is what she
What
wants.
the boss wants.
What she wants is what she gets.
I put polka dots on there for you.
Hey, shush. Hi, Cheyenne. I was out talking to the painters. What you got?
Okay, so I
Right.
know you showed me step by step, but when I tried to
Right.
do, okay, this is for part F of number 7. I tried to plug
Yeah.
it in. I got lost somewhere plugging it in for the T multiplier. Now, I had already
Mhm.
had the answer because even though I didn't understand it yesterday, I did the read it option and that
It should.
actually
Mhm.
it gave me it gave me a chart
Uh-huh.
that actually verbatim said under like each value for DF actually gave you the interval answers.
Oh, well, that's even easier then. Do that.
Okay, because I tried to plug it in like how you had it and I couldn't figure it out, but I had the answer. I just didn't understand the.
No. Yeah, I mean, you can actually get a page. It's probably a part of a big page where it says degrees
Yes.
of freedom 5, 6, 46, 57, and then 90.
It had all the intervals and then like
97,
90,
that's the magic number.
99,
Yes.
95. It had all of that. So that's how I got the answer because I don't know what's clicking for me. But I could not.
That is clicking in the sense that it's just a magic number. Because when I say to you 1.96, isn't that just the number that you use in a normal distribution, right? If you wanted to find out where that number came from, you could actually go to a normal distribution and do the between 95 and you'd see it was 1.96 either side. In fact, you could do that with the T distribution. Let me try that for you. And maybe that would work better. So if you hold on a second while I find a salt button to work with. You salt? Yes, you are salt. Okay. Let's do distribution calculation. Just go to your T distribution. How many degrees of freedom did it say the question had? 26 or something?
For mine it was 60. For
16 or 60?
60.
Right. So you had 60 as a degree of freedom for your question, right? And what you do is you go over here and you do a between, and you make the between 95%, which is 0.95. And do you see the 2 that they're talking about? There it's there.
Yes.
So
Okay, the
it's a little bit easier that way.
it is much easier. Some just was
Okay.
not working with the math on that one. Thank you very much.
So to give you an example, since this question is here, suppose you had another story where the degrees of freedom were 67. Do you see that the magic number has changed just a little bit? It's now 1.996. And if it was just 6 people, the magic number has now changed to 2.4469. So if you set it up like that, you can get them pretty quickly, which is probably, now I've seen that, a much easier way of doing it than the way I showed.